All right, we're going to look at a bunch of examples here of finding where functions are continuous based on their equations. So we've talked about some other videos looking at graphs, and that's certainly a way you can think about these. You want to make sure that you're careful and have an accurate graph. These are slightly more complicated functions than some of the ones we looked at in the one where we used a graph. So we're going to just talk about these in terms of equations. The first thing I want you to notice is that none of these examples are piecewise functions. None of these examples are piecewise functions. So I don't really have to worry about the different pieces of a piecewise functions that may or may not meet up at the same place. So when I'm thinking about functions that are not piecewise functions or have similar type graph to piecewise functions, really, when I think about where these functions are continuous, really, all I need to think about for these kinds of problems is domain. Continuity and domain are not the same thing, but for these kinds of functions, that's really the only place you're going to have trouble with continuity. So when we're asked to state the intervals on which these functions are continuous, our answers are actually going to be the same as if the question asked us to state the intervals on which the function is defined or state the intervals that are in the domain of the function. For these problems only. Okay, so domain is a college algebra or pre-calculus kind of idea. So you did that before. Not everybody remembers it perfectly, so we're going to review some of that as we go through here. All right, so for functions, there are three main things that we will need to worry about, and then one more if you include trig functions. But three main things that we will need to worry about in terms of where a function is continuous or not continuous. Again, we're really thinking about domain. One of them is denominators. So we want to remember that we want a denominator to never equal 0 because anything over 0 is undefined. So that's not part of the domain of the function. So you might notice that we have a few functions here with denominators. So we'll have to think about the denominator being 0 for each of these. So I'm just going to summarize over here. Denominator not equal to 0 is one important thing I want to pay attention to. One other thing that you want to pay attention to is that you want to make sure that you're not taking the square root of a negative number. Square root of a negative number is an imaginary number, which sometimes have applications, but in terms of domain and range of functions for calculus, we don't want imaginary numbers for the output of the function. So when I have square roots or even index roots, so fourth roots, sixth roots, things like that, we have to be careful to make sure that the quantity inside the square root should not be negative. So I want the stuff inside the radical to be not negative. Inside a square root to not be negative. So that's two of the four things that you ever have to worry about for function domain. The third thing that has to do with function domain is logarithms. So the issue with logarithms is, again, that like square roots, you can take logarithms of negative numbers, but they're imaginary outputs. So in general, we don't want those when we're talking about functions that we're going to do calculus with. So for logarithms, we don't want to be taking the logarithm of something that's negative. So I don't want this expression inside of a logarithm to be negative. And I also don't want it to be 0. I can take a square root of 0. Square root of 0 is 0. But a logarithm of 0 is undefined. It just goes back to the definition of what a logarithm is. So I want, when I think about logarithm functions, I want the stuff inside there to not be 0 and also not be negative. Okay, if you include trigonometric functions, there are some other things to think about with domain, but we are not dealing with trigonometric functions in this class, so I'm not going to include that in my list over here. All right, so when I'm thinking about the intervals on which any of these functions are continuous, I'm really going to start by thinking about domain. All right, so for this first function, I'm kind of going through my little mental checklist, which hopefully is in there from algebra somewhere, even if it's not fresh in the front of your brain. Hopefully it's coming back. I know you've done that before in whatever algebra class you had before. So in this one, I would first of all just notice that I have a denominator, and that's really the only issue. I don't have any square roots. I don't have any logarithms. So this denominator is really the only thing I have to worry about here. So I want to avoid any values of x that would make that denominator equal to 0. This is a simple enough denominator. You can probably just look at it and think about the x value that you would plug in that would make that denominator be 0. That's a problem. If not, if it's a little more complicated, like this denominator here, you can set the denominator equal to 0 and solve for x. I'm not going to write that down here just to save space, but I could write x minus 2 equals 0 and solve for x. I would get the value that I want to avoid. So I want to avoid x equals 2, because that would make this denominator 0. So when I'm asked to state the intervals on which the function is continuous, and again, for these problems, that's really just about domain, I'm going to state the intervals that avoid 2, x equals 2. So I'm visualizing a number line. I'm thinking about I want everything except 2. So that splits the number line into 2 intervals, one on one side of 2 and one on the other side of 2. And so I'm just going to write those 2 intervals down. So one interval would be from -infinity to 2, and then another interval from 2 to infinity. And again, you can use the union symbol here. It looks like a U in between, which means this or this interval or this. I don't care if when you write things you put a comma in your online homework. You might need to put the union symbol in order for it to count that correct. All right, so denominator was the only thing I had to worry about in this one. All right, this next one, denominators, no. Square roots, no. Logarithms, no. Trig functions, no. So this one, I have nothing that would cause restrictions on the domain. So there are no x values I need to avoid on this one. This is a polynomial function. If you remember that kind of vocabulary, polynomial functions could have higher powers than this. This is a degree 3 polynomial. But polynomial functions don't have any of these things in them. And so polynomial functions are continuous everywhere. So the interval that would describe everywhere is the interval -infinity to infinity. Again, I'm thinking through this list. None of those things apply to this problem, so I don't have any x values I need to avoid, so my interval is just -infinity to infinity. Okay, so e to the x function. So I could think about the graph of this one. This one is one that's pretty simple. Maybe you know the graph of that one, and that can help you think about that too. But let's just kind of focus on the equation and think about these things. So denominator, no. Square roots, no. Logarithms. This is related to a logarithm, but this function is actually the inverse of the logarithm function. It is not the same as the logarithm function. So logarithm functions do have restrictions. Part of the reason they have restrictions has to do with the output values of this function, but this is not the same as a logarithm function. So sometimes students get that a little bit mixed up because they think this is related to the logarithm. They think it's the same as the logarithm, but it's not. So this, again, has none of these issues in it that would cause any trouble with any values of x that I would need to avoid. So on this one, no values of x that I need to avoid, which means this function is continuous everywhere. So -infinity to infinity. All right, a few more over here. So k of x function, I don't have a denominator. I do have a square root. I need to ensure that that expression inside that square root is not negative. I don't have a logarithm. So it's really just the expression inside the square root that I need to deal with. So there are a couple of ways to think about writing out work. If you need to write out work, to think about what x values are allowed or not allowed. Here, I wrote the values of x that I want to avoid. Another way to write that would be to figure out the values of x that are okay. And so that's actually what I'm going to write on this one. You could write the work for the problems differently. And either way, you can write down the same answer. But in this one, if I want the expression inside the radical to be not negative, then that means I want the expression inside the radical to be 0 or positive. So 0 or positive is OK inside the radical. You just want the stuff inside the radical to not be negative. So that means it could be 0 or positive. All right, so for my little scratch work here, I'm just going to write 4x plus 3 could be equal to 0 or positive. So that would be greater than 0. So I can write down a little inequality, 4x plus 3 greater than or equal to 0, and then solve for x. So just to save space, I'm not going to write out those algebra steps, but I'll talk through them. You would subtract 3 from both sides. So you'd have 4x is greater than or equal to negative 3, and then divide through by 4. So you'd end up with x is greater than or equal to negative 3/4. Right, so that's written as an inequality. We were asked here about intervals, so I'll go ahead and write that as an interval. If you're not specifically asked for intervals, you're just asked where is the function continuous, it would be okay to leave it like this, but often in your homework you're going to be asked for intervals. All right, so for this one, x can equal negative 3/4, and then I want to be bigger than negative 3/4. So I'm going to use a closed off bracket to indicate equal to negative 3/4, that it can actually equal that, as opposed to these rounded brackets, which indicate x can't equal that value. And then greater than that would take us to positive infinity. So that's the interval for this one. All right, these last two have sort of multiple issues in them that you have to be careful about. And so some of the kind of more challenging problems after the first few in homework are like this, where you have just more things to think about, more than one of these things on the list to worry about. Okay, so on number 5, you might notice that I have a denominator that should be not 0. So I have some x values I need to avoid for that denominator, avoid values of x that will make that denominator 0. You can maybe think through in your head what those values of x are that would make this denominator 0. If not, you can write down x squared minus 4 equals 0 and solve for x. You could add 4 to both sides and then square root both sides. And don't forget the plus or minus. You get x equals plus or minus 2. So I have to avoid these values of x. So my intervals will exclude both x equals 2 and negative 2 from the denominator. I also have a radical, and so I need to make sure that that expression inside the radical is not negative. So with the radical ones, I tend to like to write it like I did here. And so I might write that that expression inside the radical has to be greater than or equal to 0. And that would tell us that x is greater than or equal to negative 9. All right, so there's a lot going on here that I need to think about when I write these intervals. I would visualize a number line. When you read a number line, you want to read it left to right, just like you read a sentence. So I would think about on the left side of the number line, I'd be coming along until I get to x equals negative 9. So I don't want any values that are less than negative 9. I just want x values that are greater than or equal to negative 9. So visualizing the number line, the first x value I would get to is negative 9. And x can equal negative 9. And then as I come along that number line, when I get to x equals negative 2, I need to exclude that. So this would be from x equals negative 9 to x equals 2. If it helps you to draw a number line with these inequalities, you could do that as well. Negative 9 to negative 2, and then exclude negative 2. And then I can be on the other side of negative 2, though. It's just like you pluck that point at negative 2 out of that number line. So you're going to come up to negative 2, pluck that point out, and then on the other side of negative 2, you'll go from negative 2 to positive 2. Pluck out that point at x equals positive 2. And then from there, you can go from 2 to infinity. All right, so this one's got 3 different separate intervals where that function is continuous. So again, maybe drawing the number line helps you visualize this if you have a little bit of difficulty with intervals. All right, one last one here. So thinking through these items on my domain list, which again, hopefully is in your brain somewhere from college algebra. Hopefully this is not new information to you. So I have a denominator, so I want to avoid x equals 0. Any values that would make that denominator 0, that's the only one that would make that denominator 0. And then on this logarithm one, I want to make sure that the expression inside the logarithm is not 0 and not negative. So similar to what I do with the radicals, I tend to think about the logarithm, and in terms of thinking about what I don't want it to be, I switch that around and I think a little bit about what is okay for that to be. So if a value is not 0 and not negative, then it's okay if you have ln of a positive. Positive inside the logarithm function is okay. So positive would mean greater than 0. So I want to avoid x equals 0, and then I want this expression inside the logarithm, 2x minus 1, to be positive or greater than 0. So sometimes you can just think about the numbers, but if not, you can write this inequality and then solve it for x to think about what is okay. So if I add 1 and divide through by 2, I get x is greater than 1/2. Okay, so now I want to think about this and what I'm going to write down for my intervals here. So I'm going to go ahead and sketch this. I mentioned that sometimes drawing a sketch is helpful. So the first one says that x has to be greater, the one I have on top, x has to be greater than 1/2. All right, so I'm just going to draw a little number line. So x greater than 1/2 would be at x equals 1/2 and then right of that. Okay, so that first inequality that I have written down there says x greater than 1/2. So these are values that are okay. And then when I look at the denominator, it says I need to avoid x equals 0. Okay, so in this one, although I have really two different things to think about when I think about restrictions on x for this function, one of them sort of takes care of the other. Notice that if x is greater than 1/2, then it can't be 0. So sometimes students get the mistaken idea from a problem like 5 that you got 3 numbers here, -9, 2, and -2, and that's going to set up your intervals. So if you're having trouble with intervals, again, sketching that number line can sometimes help. X greater than 1/2 also does avoid x equals 0, so I don't need to list that separately. So on this one, I will just write 1/2 to infinity for my interval. All right, these problems tend to not be easy. They require that you remember a lot of different stuff from algebra, so it's okay if you're struggling and need to review some of that stuff, but please just come get some help from me, go see a tutor, ask someone who knows what they're doing with the thinking about the algebra functions and thinking about domain and continuity. It is okay if these are a little bit hard for you, but just keep practicing them and they will get easier.